I forgot to point out in the at the end of the previous video, let's look back at U-substitution versus reverse or trig substitution. In U-substitution, the new variable is a function of the original variable, u equals 1 minus x squared. In reverse substitution, now the new variable, theta, is giving us values of x, kind of. We're saying the old variable, x, is a function of the new variable, rather than the new variable being a function of the old variable. So let's go on to the next big problem, which is integrating a semicircle, which is something we actually don't know how to do yet, but here's our big chance. First, can you write the formula for the unit circle in terms of x and y? So try to do that before I do that, or pause the video. It's x squared plus y squared equals 1, right? Or if you solve it for y, you get y equals root 1 minus x squared. And I get a semicircle like that. And let's say we want to take a slice of it from A to B. We actually don't know yet how to find that area, but that's what we're about to do. So we want to say, what's the integral? Let's ignore the a and b now for now, just focus on the indefinite integral. Integral of 1 minus x squared dx. I'm thinking maybe a trig substitution. Would the same one we did last time still work, do you think? Well, let's write it down, give it a try. We'll say x equals sine theta, dx equals cosine theta d theta. And we know later when we back substitute, we're going to want to be able to say what is theta in terms of x. So we'll just write that here while it's handy. Arc sine x equals theta. All right, so let's substitute in the integral here. So square root of 1 minus sine squared theta cosine theta d theta. Pretty much what we did last time. So the next step is just some trig stuff, so go ahead and do that and come back when you're ready. All right, welcome back. So we'll have this turns into cosine squared theta cosine theta d theta, and then cancel the square with the square root, so we get cosine theta times cosine theta d theta, which is integral of cosine squared theta d theta. So it didn't all nicely cancel like the last time, and we have to do a bit more thinking. Can we just integrate cosine squared all by itself? Can I use the power rule? Turns out no, that only works for like x squared dx with no cosine in it. Let's write that down. We can't do like 1/3 cosine cubed theta. You could try checking that if you want, and you'll find out with the chain rule and everything, it just doesn't work. Instead, we have to use a trig identity, which we wrote in our reminders of trig identities, that cosine squared is 1/2 plus 1/2 cosine 2 theta. So let's write that trig identity, 1/2 plus 1/2 cosine 2 theta. And now can we integrate this? It's not so bad. What's the integral of 1/2 x? It's 1/2, oh sorry, what's the integral of 1/2 dx? That would be 1/2 x. But this isn't dx, it's d theta, so we'd get a 1/2 theta. We'll copy this 1/2. Then what's the integral of cosine? It's sine. Copy the 2 theta. And then we're kind of implicitly doing a U substitution, or you could call it one of the big 4 shortcuts. Whatever frequency this is gets divided by over there. And we're done with the integral. And then we should back substitute, right? So the theta, we know that theta is equal to arc sine of x. And then we'll have the 1/2 sine 2, and then the theta becomes arc sine of x times 1/2. plus c. And at this point, all the calculus is done. We can type this into Desmos, and maybe we'll go do that and make sure that its derivative is the square root of 1 over 1 minus x squared. But don't think that this video is done. There's more interesting stuff to do. A lot of people like to simplify this so it involves something about square root. So let's go check what we have so far before we do anything more complicated. So here I've got my semicircle formula, root of 1 minus x squared. Does this look like a semicircle? It looks kind of squished to me. We have to think about what's the aspect ratio of our graph. -1 to 1 on the y-axis takes up a whole lot less vertical space than -1 to 1 on the x-axis. So I could try zooming like this until it looks kind of semicircular. It's not a bad idea, but it's nice that Desmos actually has a little zoom square thing that makes sure that the aspect ratio is square. And then sure enough, that does look like a semicircle. I can zoom out a bit evenly on both axes and it'll still stay square. So that's nice. And then here's the antiderivative we got with only basic back substituting. And let's check that its derivative actually matches the semicircle there. So that's looking good. So let's think about that a little more carefully. What's the slope here? It looks like it's fairly flat, and so the slope would be 0, which would match the value of the original function here. And the same thing here, looks fairly flat there, and so its slope would be 0, and this has a value of 0. Here this has a slope that's pretty much 1, and this has a value of 1, so everything is looking good there. So let's go try some other kind of simplifying on that formula. So let's follow tradition here and try to simplify this sine of 2 arcsine of x. It feels a little silly to take the arcsine of something and then take the sine of it. It would be nice if we could move that 2 multiplier out in front and just say this is 2 sine of arcsine, because then sine cancels arcsine and it would just be 2x, but that's just not right. It just doesn't happen that way. What can we do? Well, we have sine of 2 times something, and we have a trig identity about that. So remember we have sine of, let's say, 2 happy face equals 2, so I don't want to use theta because we used theta above already. I'm just saying 2 times anything here gives you 2 sine happy face times cosine happy face. So here happy face is arcsine x. So we'll say this sine of 2 arcsine x is equal to 2 times sine of arcsine x times cosine of arcsine x. Can we do anything with that? Well, sine of arcsine, that we can replace with x. And then what can we do with cosine of arcsine of x? Well, here's where we actually need to start drawing triangles again. Let's draw a right triangle. We'll put theta here in the corner, and let's use a hypotenuse of 1 because we've been doing the unit circle. And what is, if I have theta here and 1 here, and we've said that x equals sine theta, sine would be over here because it's the opposite over the hypotenuse. So we could say x, which is sine theta, since sine is opposite over hypotenuse. I'll put a colon there. Sine is opposite over hypotenuse. And this is the opposite side from the theta there. And what else can we say? If that side is sine, this side is cosine. We could say it's a 1 times, because if that hypotenuse was longer, then if it was like 10 times longer, then this would be 10 times longer, and that would be 10 times longer. So this is basically our kind of first right triangle that we draw in trig class, right? then what else can we say about it? Well, I know that's 1 and that's x, and I can use the Pythagorean theorem to say what this side would be, right? So we know that this side squared plus that side squared equals 1. So I could say this side is root 1 minus x squared, or 1 squared minus x squared, because I know the hypotenuse is 1 and this side length is x. So I can kind of back solve in the Pythagorean theorem to get that. So this says that cosine in this situation is 1 over root root 1 minus x squared. And so I can substitute arcsine of x is another, you could say, is theta, right? We said that way up here. Arcsine of x is theta. And cosine of that would be root 1 squared minus x squared. So all this stuff is 2 times x times, instead of cosine of arcsine of x, we can say just square root of 1 minus x squared. And so that puts it back in terms of the formula we started the integral with, which is kind of nice. Remember, this was just a small part, or just a part of what we started with. So let's go back and write it all together. Capital F of x equals 1/2 arcsine x plus that part, 1/2, and then this sine of arcsine ended up with a 2 there, so we can cancel those, and then we get that, and then that. Oh, sorry. All right, so finally we have a way to take the antiderivative of the unit semicircle, and we can find areas under that circle or semicircle. What's left to do? Graphing and making sure that this works the same as our other antiderivative, and also taking the derivative by hand to check. That's its own interesting path, and we'll do that in the next video.